next presenter is Justin Kang.
How's that? Hi, everyone. Hi. So my name is Justin, and today I'm going to be presenting our work, The Fair Value of Data Under Heterogeneous Privacy Constraints in Federated Learning. So the crux of this work is really studying the relationship between the online platforms and users. Users are typically data generators, and they send their data to the platform with some privacy level. So they may request that their data is encrypted, or that their data is treated with differential privacy, or perhaps they may only allow their data to be used in a federated learning setting. And the platform's goal is to take this data and turn it into utility to make money, right? And we might hope that in exchange for providing all this data to the platform, there's some kind of compensation for the users, right? So this could be access to services, discounts, or even money. This is a formal setup of our setting. So we have n users, and each of these users receives some payment, phi I, as well as has some privacy sensitivity, ci. And what they're trying to do is they're trying to choose their privacy level to maximize this difference. So they want to maximize their benefit minus this privacy cost that they feel. So they choose the privacy level in this way. And we're using epsilon I to represent the privacy level. So you can think of this as a DP parameter if you're familiar with DP, or more generally, it can just be some scalar that represents your privacy level choice. So you can also think of this, say, as some binary variable that says whether or not you're turning on or off your location history or something like that. And all this data gets sent to the platform, and the platform performs some privacy level respecting algorithm to generate some utility, right? And the platform's goal is obviously to maximize its utility minus the sum of payments that it makes to the users. And in order to maximize this, the platform controls the payment system. So the platform is able to modify this payment system to try to maximize this quantity. Now, in the literature, this problem has been studied, and it's known as the optimal data acquisition problem. There's an excellent body of literature on this work. And we wanted to take a bit of a different approach, and we wanted to try to understand how does fairness fit into data acquisition. So the notion of fairness that we settled on is the Shapley value from game theory. The Shapley value is an axiomatic framework that depends on 3 key axioms. The first axiom is the fairness axiom, which says that if you have any 2 users that have the same value to the platform at each privacy level, then they should be paid roughly the same, right? And the second axiom is the linearity axiom, which says that when the platform is trying to combine 2 independent tasks, the incentives for the combined tasks should just be the sum of incentives for the individual tasks. And then finally, we need some normalization here, so we have this kind of efficiency assumption, which says the sum of all the payments made is some alpha fraction of the total utility. So if we have phi i's that satisfy all 3 of these axioms, it turns out that they actually are uniquely determined. And this is that form. So the platform receives obviously 1 minus alpha times the total utility, while each of the users receives phi I, which is this weighted average of their marginal contribution. So averaging over all the possible subsets of users, when you add the ith user, how much extra is the utility going up? Now, this is a really cool example where we calculated the Shapley value in this federated mean estimation problem, so I wanted to share this with you guys. The setting is the users have 3 privacy level choices. One, they can choose to not participate at all. They send no data to the platform. The other is they all securely aggregate their data together. So with everyone that chooses this privacy level, they securely aggregate and then send that data to the platform. And then there's this final choice where they can just send their data directly to the platform. And in addition to each user choosing one of these privacy levels, they also have each a different amount of data. So we went ahead and calculated the Shapley values for this particular problem, and the results were really interesting. So what I've plotted here on the left is the difference from even split for a few of the users. And there's some really interesting phenomena going on here in that we get quite different results if the data distributions for each user is heterogeneous, so there's like a big difference between the means and variances of the users, or it's a more homogeneous setting. And the upshot of this is basically saying that the Shapley value is characterizing some very complicated notion of fairness, and that if you try to introduce some simple notion just based entirely on the privacy level or entirely on the data, you're really missing out on some very important aspects of fairness, right? And so now that we have this great notion of fairness, the next question is, how does the data acquisition problem change when we constrain the platform to sort of act fairly? And this is how we've chosen to formulate this data acquisition problem. In this formal setting, we're restricting to binary privacy decisions. So either you choose to share your history or you don't choose to share your history. There's one low privacy option and one high privacy option. And the platform must use the Shapley value, but it's allowed to change its alpha. So that's how it has input into the system. And we modeled the user behavior using the game theoretic concept of the Nash equilibrium. And it turns out in this setting, we can derive a formal theorem for the optimal choice of alpha that the platform should take. Now, I'm not going to go over the theorem, but instead I'm going to show you this figure which does a good job at highlighting the overall results of the theorem. And the result is that there's essentially three key regimes. The first is when the user privacy sensitivities tend to be low, the optimal thing for the platform to do is to raise the incentives high enough such that all the users choose to participate at the low privacy option, and the utility that the platform can achieve is kind of maximized in that setting because everyone's giving as much data as they can at the lowest privacy setting. And then there's a threshold beyond which the optimal strategy for the platform is to set the incentives high, but not high enough so that everyone always chooses to participate at the lowest privacy level, and instead they play a mixed strategy. If you don't know what a mixed strategy is, I think we can interpret that to kind of mean that essentially they're setting the privacy level such that some fraction of the users are choosing the low privacy option and some are choosing the higher privacy option. And then finally, eventually there's another threshold beyond which it's no longer worthwhile for the platform to try to undergo this task and generate some utility. So everyone's too privacy conscious, and the best thing to do is just set the incentives to 0 and let everyone choose the high privacy option. So that's what I wanted to share with you guys. This has been more of a conceptual work, and you can see this some of the results I've shown here in an upcoming work that's just recently been accepted to TMLR. And one thing I didn't mention is that computing the Shapley values can be quite difficult. And this is something we've made a lot of progress on and are excited to share soon. So we've been using some ideas from sparse graph coding and group testing to compute these Shapley values. So keep an eye out in the next couple of months on arXiv if you're interested in that kind of thing. And finally, I'll just say, we're really excited to see how, going forward, fairness can be incorporated into these data acquisition problems, and particularly understanding the impact that fairness will have on, fairness in incentives in particular will have on practical federated learning problems. So, thank you.
Thanks. Any questions? So one question that I have is, so you've been talking about mean estimation.
Yeah.
Is that extendable to other operations or even gradient descent like what people use in federated learning?
Yeah, I think so. The challenge then becomes computing the Shapley values. It gets more and more difficult. So this mean estimation problem, everything is analytically tractable, and so that's what we have in this paper. But going forward with better tools to compute the values, I think that dealing with more complicated settings is definitely on the horizon.
Okay, thank you.
Yeah.
Thanks.
Thank you.
Do you have the next presenter?